Today is David Gross, speaking on marginal entropies for causal inference and quantum non-locality.
Thanks, Hila. Okay, good morning, everybody. Thanks for showing up at a time where I would normally not show up for a conference. Good move from putting me into the first slot. Yeah, thanks to the organizers, not only for that cunning move, but also for putting together this conference. Some speakers indicated that they didn't quite know why they were invited to speak here. I think I knew perfectly well why I was invited, because I had the pleasure of working a bit with Matthias on his projects. I chose, however, to make things a bit more adventurous and talk about something completely different. It's another topic we're working on now that has contained the word quantum and marginal. It's a bit, however, along different lines than the talks we heard yesterday. Yeah, what I'm presenting here is joint work mainly with Rafael Chavez and Lukas Luft in Freiburg. Here's my outline. I want to introduce a problem which I think most members of the audience are absolutely not familiar with, namely the problem of inferring causal structures from statistical data. That will be the first part of my talk. Then I will tell you how one formulation of this problem leads to an entropic marginal problem. I will present some results and state many open problems. It's a relatively young field, so there's much to say on the final bullet point as compared to the next to last bullet point. I have a few principles in life. I never crack entanglement jokes, and I never present XKCD comics in talks because that's too nerdy even by my standards. However, I don't adhere normally to my standards. So here, let's introduce the science of inferring causal structures. So we have a guy here confessing that he used to think that correlation implied causation, but he doesn't do that anymore because he took the statistics class, and the partner is offering, sounds like the class helped, and he says, yes, well, maybe. And so there is this common conception that causation cannot be learned from data, that causal connections can't be inferred from empirical observations. And this has been a bit, in the past 15 years apparently, the consensus has changed a bit, and there's now a field for people to try to find a mathematical theory of inferring causation, and I will spend some time introducing these ideas. Okay, so the general reference for the first part of my talk is this book by Pearl, who was one of a handful of people who introduced single-handedly this concept, I think, into statistics. And okay, so we want to consider a case where we have a few observations, a few random variables. For example, we could draw members from a population, the United Kingdom, this audience, and we would sometimes observe incidences of hay fever or of cold. Some people would have a tendency of sneezing, and others would have a tendency of wiping their noses. And we would see certain correlations and certain independences between these random variables. And us understanding how the world works, at least in parts, we'd have a plausible assumption of how the causal process underlying these data could look like. Namely, we could think that hay fever and cold are at the root of this causal tree, and they would make people sneeze, and if people sneeze, then they would wipe their noses. We would find it unlikely, for example, that wiping one's nose would create us catching a cold, would cause us catching a cold. And the question is, can we actually, without our world knowledge, infer the structure from the observations? So let's formalize this a bit. So what we have is we have a situation where we have n variables, x1 to xn, and then a causal structure is, as indicated here, given by a directed acyclic graph connecting causes to effects, and the interpretation more formally would be that the ith variable is a deterministic function. Xi is a deterministic function fi of its parents. So sneezing is a deterministic function of hay fever and cold, and maybe some independent random variables which are local to this node. Right? So that is that would be the formalization of how to read these directed acyclic graphs. And of course, again, I say it again, the central question is, can one recover this causal structure, which are indicated here, just from empirical observations about correlations found in this population? And yeah, to connect back to this initial comic strip, of course, for example, the question would be, can we actually prove that sneezing, a propensity for sneezing, causes a habit of wiping one's nose, or if I wipe my nose often enough, will I then start sneezing suddenly? Can we decide which of these two errors is the correct interpretation?
You can have an edge in both directions going between two nodes.
Aha, okay, so my class here are acyclic. Yes. So that's part of what I want to have in the causal. Yeah. And it's not clear that this captures all situations.
Right.
But in the real world, things reinforce each other.
Okay, that's exactly. So that's why we start modest, and let's see. Assuming that there is such a linear directed structure that could explain my data, can I then find it? And sometimes I will not be able to, particular maybe because there are feedback loops.
Yeah, because you can have a two-way with two arrows, no? You can make a bidirectional one.
Oh yeah, I mean absolutely, and people do, by the way, right? Okay, so this is Causal Inference Chapter 1, and there's Chapter 2. I won't get there.
You can simulate that, yeah.
But I mean, even if I do assume that there is a linear relationship or a tree-like relationship, then even then it's unclear whether, from observation of these correlations, I will be able to tell the direction, right? And until 15 years ago, people would have outright said this is impossible, and since the mid-90s, the answer is a cautionary yes. So there are circumstances under which one can actually infer it, and in particular, we'll see that in our model, we can actually, from observations, argue that sneezing should cause wiping and not the other way around. In order to explain how this works, there are two ingredients. One is a bit more rigorous than the other. So one is called the local Markov condition, and the other one is a minimality principle. So let's introduce these two ingredients that people use to argue for inferring causal structures. All right, so let's see, what are the observational corollaries of this structure? What is it that if I assume that this structure is the correct one, what properties will it cause my observable random variables to have? And the property is called, one of the properties is called the local Markov condition, which means that for every random variable I, it's true that xi is independent of its non-descendants given its parents. So for example, if I look at the wiping one's nose random variable, if I condition on sneezing, then it will be independent of whether I have hay fever or I have a cold. So I can kind of disconnect the graph theoretical future from the graph theoretical past if I condition on all nodes in between. That's basically what it says, right? So there is no the cause is mediated by this middle variable. There's no direct connection, right? And so this that's what I said. So this is a property and a conditional independence that is observable from the random variables in principle. So it gives me a criterion for rejecting a causal structure. If I find this local Markov condition violated in my data, I can reject that explanation, right? So for example, if I were to find that wiping was not independent of cold given sneezing, then I know immediately that there must be some other causal pathway between having a cold and wiping my nose that does not feature here, so I could reject that structure. So, so the first lesson to learn here already is that empirically observed conditional independences hold some clue about causation, right? At least in a negative way. It allows me to discard certain causal structures. So it is this way of thinking that will be important for what comes later. There is a strengthening of this principle one can employ which is employed by actual causal inference algorithms. We won't actually use that in the future of the talk, but I anyway wanted to present one or two slides on it, so to tell you how people who actually use this on data sets, how they argue. And the need for an additional assumption comes from this the trivial example that should be kind of a bad news for the program, namely every data I observe is compatible with one unobserved universal cause. So there could be one unobserved node here, which in quantum non-locality people would normally call a hidden variable. In statistics, it would be called a confounder. So something that I don't see, which influences all the variables I have, right? So some god tells me that some people have hay fever, some people have a cold, some people sneeze, and some wipe their noses. And that seems to be bad news for the program of discovering causal mechanisms, because any causal discovery algorithm could just always give this answer, namely there is God and he decides and there's nothing else to worry about. And so in order to get an interesting theory, one needs to add an additional principle that excludes these act of God type solutions, that is defendable, that is plausible, and also it should have a pleasant sounding name to compensate for the lack of being provable. Right? This community came up with a principle checking all these three bullet points. It's called Reichenbach's principle, so pleasant sounding indeed. And it goes by many different names. Some call it minimality or no fine-tuning. Some people say it's a version of Occam's razor. And one of its incarnations is the following. It says that all observed independences should result from the causal structure and not from coincidences. So let me say what I mean by that. So if we assume that this is indeed the causal structure that gives rise to my observed data, then I would generically, for a generic dependency of these variables on this unknown data, on this unknown hidden variable, and for a generic distribution of this hidden variable, I would expect to see no independences whatsoever. Right? If I formalize this in any sensible way and I draw all these components randomly, then I would always have dependencies between any pair of random variables, which is not what I see. So, for example, if we observe that hay fever and cold are independent in our sample, then this would require a fine-tuning of the parameters of this process to mask the fact that they actually have a common history. And now the assumption, plausible or not, judge for yourself, that is made in all these discovery algorithms is that we do not assume this happens. We assume that everything we see in the way of dependencies and independences has a structural cause, has a structural reason. And so we would reject this explanation of the independence relations we see by invoking this unprovable but pleasantly sounding Reichenbach's principle. And of course, one has to keep in mind, this might seem a bit ad hoc, but one has to keep in mind that we're talking about statistics, and statistics is always fraught a bit with insecurity, and it's full of these principles that people have to invoke in order to do something, because the alternative would be just giving up. For example, that estimators should be unbiased or have minimal variance is also not justifiable really from any these are likewise ad hoc principles that seem to work well in practice. Okay, so let's put this Reichenbach's principle to use and try to find whether we would start sneezing if we just started to wipe our noses often enough. And so let's say we have some data set, and the data set displays all the independences and dependencies that are compatible with this causal structure. So then the question is, can we recover the causal structure uniquely? The answer turns out to be no. But can we recover some features of it? And the answer turns out to be yes. And so I'm not going to prove it, but let's look at some examples. So for example, somebody could say, yeah, hay fever and cold probably cause you to sneeze, but I think sneezing is also a consequence of wiping one's nose. So somebody could defend this point of view as the mechanism that gave rise to the data. And we can reject this, and the reason is that if sneezing were a common cause, a common effect, were effect of all these causes, then in general, if I conditioned on sneezing, these would be dependent, right? So, for example, let's say this is some random variable which takes on the value 1 if all its inputs are the same, and 0 if they're distinct. Then if I condition on this being 1, obviously the causes become dependent, right? So we can reject this because in general the structure would predict dependencies which we don't observe here. We can also say, yeah, maybe there's some hidden variable, some unobserved effect which makes you both sneeze and wipe your nose. But we can also reject this because this would, for example, mean then that wiping would be independent of hay fever, which it is not. There are other causal structures which are compatible with the observations. For example, there could be an unknown common cause both to having a cold and to sneeze, even though there is no direct connection, and this turns out to replicate the same correlations. So we can't actually recover that causal structure, but one can make an exhaustive list or do some relatively simple argument, and in the end come to the conclusion that every eligible structure that predicts exactly the observed dependencies and not more actually includes the error that sneezing causes wiping and not the other way around. So there is actually a way of at least certifying this this error from data, which I guess came to a surprise to people engaging in statistics until 15 years ago or so. All right, okay, so let's move a bit ahead also to get to entropies and marginals, because these haven't featured yet. So I argued now in the beginning exclusively in terms of dependencies and independencies, and there is one can show that if all variables are observable, then this is actually all you ever have to look at. So any causal structure you can infer from the data can be inferred from just the dependence and independence relations. And the situation becomes much more interesting if only a certain subset of the variables is observable. So we only have access to marginals. And here is one problem, a common ancestor problem. So the way to interpret that here, that I have three observable random variables, A, B, and C, and I have two hypotheses. For example, I can think this is like the universal scenario I had at the beginning. So there's one global hidden cause of everything I see, or maybe I'm a bit more economic and I think, well, maybe the correlations I see could be explained by assuming just pairwise path interactions, but no joint path interactions. So not every, but of course these lambdas are invisible to me, I have no access to them. Now not every marginal distribution I can see in the A, B, and C variables is compatible with the structure. For example, if, I have it here, for example, if these are three perfectly correlated coins, then it's easy to see that I cannot create such a distribution by assuming just pairwise path interactions. Right? If they are perfectly correlated, there is no way to also get these perfectly correlated unless all of them share a common history. So there is, so looking at the marginals, at the accessible marginals, A, B, and C, I can also reject some causal structures, even though the set of independences between A, B, and C is the same in both situations, right? So the initial program of just looking at conditional independences is very successful in some model situations, but it fails in more general situations. All right, so the challenge now is to describe the marginals of a general causal structure in such a way that if I have a set of data, I can test compatibility with a presumed global causal structure. And this turned out to be difficult, these marginals in general, because these independence assumptions, they are of algebraic nature. So we get fairly difficult non-convex sets. There is a program, and I think Joseph Landsberg maybe could tell us more about it, of algebraic statistics of people who try to make this, to describe these sets. And I'm sure it's a successful program, but maybe you won't contradict me that being with Kröpner basis being what X space complete, it's very difficult to get computationally tractable criteria out of that. And I have this figure here, which I like for various reasons. So that's some marginal, well, a cut to some observable marginal distribution conditioned on some causal structure. You see it looks more like an algebraic variety than these convex polytopes, maybe people studying marginals in terms of in the context of quantum non-locality are used to, and that's why I like it. I like it for other reasons. I like it because so it studies some very applied problem. It studies the problem of detecting a phenomenon called homophilia in social networks, and the question is if we see that people befriend each other that have common traits, is that what is the cause and what is the effect here? Do they become friends because they are similar, or do they become similar because they are friends? And there's a big discussion if we can distinguish that from social network data. And the authors here of this paper, where they provided a new hierarchy of convex relaxations for identifying these regions, they have a blog post about their paper, and it's called Bell Inequalities for Social Networks, and they are very much aware also of the quantum theory. So, so in a minute I will connect the two things. I mean, these are these marginal problems, of course, are very, very like in spirit to Bell inequalities. Okay, but the main point is these marginals are complicated, and so let's maybe summarize the situation here. If I know the marginals and I have no causal constraints, then I'm in the situation that has been studied in quantum non-locality for a long time, and the marginals will be polytopes, and these are often referred to as Bell polytopes. If I go to the other extreme, if I have no marginals, so I observe all the random variables, but I have causal constraint, then I'm back to this Pearl scenario I started my presentation with. So then it's also relatively simple to describe these marginals because they are characterized just by their conditional independences. And if I have something in between, if I have marginals, and I have also causal constraints, then things are difficult, and arguably that's a field where new ideas are still required. And the one ansatz I'm going to talk about today is to use information theoretic methods, and the idea is that conditional independences are algebraic constraints on probability distributions, but they are linear on the level of entropies. So that motivates looking for entropic characterizations of marginals subject to causality constraints. Right? If we understand the global set of entropies, then adding causal constraints does not make that object much more difficult.
What is entropic?
Yeah, I'll come to that in the next slide. And yeah, so in terms of joint entropies. And this way of thought, which I will explain on my next slide, has been discovered independently in two different communities, namely in the machine learning community by Bastian Steudel and Nihat Ai in 2010, and simultaneously by a bunch of quantum people, namely Tobias Fritz, Rafael Chavez, and now also Lukas Luft and myself since a few weeks. And so I think, yeah, one thing that I like about this is that two people with very different backgrounds seem to have started working on these problems at the same time. Okay, so now I prepared some slides for you. What do I actually mean by that? So I can set up now the mathematical context in three simple steps. Here's the first step. And the first step is to talk about the global unconstrained object of joint entropies. And what I do is, it's very simple. I pick some probability distribution, some joint distribution of n random variables, and then with every subset S of these variables, I can associate the joint entropy. And I can do this for every subset, so I can collect all this information in some entropy vector, and it's a vector in r to the 2 to the n, which is the number of subsets here, including the trivial subset, and this vector is naturally indexed by subsets of that set. Right? So with every probability distribution, I get this high-dimensional vector encoding all the all the joint entropies. It's very easy to see and appreciated for a long time in information theory that the set of all such entropy vectors, if I vary over all possible distributions, that it forms a convex cone up to topological closure. And the convex cone, of course, is an object that is characterized by the fact that it's closed under adding 2 points and also closed under rescaling points with a non-negative number. And that it is closed under addition is very easy, because if I have two probability distributions which map to 2 different points, I can just take the tensor product, and the entropy of the product will be the sum of the entropies, so I can add things together. Scaling is a bit more subtle. What you do in essence is you find some continuous deformation between your distribution and a trivial distribution, and the trivial or all deterministic distribution would sit down here at the apex. One has to work a bit harder to make that precise, but in essence that's what it is. And so the set of joint entropies is a convex cone. The structure of that convex cone is not fully understood. It's an area of active research, but there is a simple outer approximation to that convex cone that is often invoked, and we would sometimes, not always, sometimes work with that. And we know a bunch of linear inequalities that are valid for joint entropies. Mostly that is strong subadditivity, and also the other one is monotonicity. And we can just look at the cone of all vectors which are subject to strong subadditivity and monotonicity, and this gives us an outer approximation. Right? And we'll usually work with an outer approximation, which means all our bounds will remain valid, but they might not always be tight. Indeed. Okay, so that was step 1. Step 2 is now we can choose a candidate causal structure and add causal constraints. and this is a step that is very difficult on the level of probabilities, but it's very natural and simple here, because conditional independences can be expressed in terms of conditional mutual informations vanishing, right? So, for example, the mutual information between wiping one's nose and hay fever and having a cold, speaking of, conditioned on sneezing should be 0, right? So that is one entropic corollary of that structure. And what is nice, maybe what we can do in that framework easily, which is not so easy to do, for example, on probabilities, is we can also relax and say, instead of demanding strict independence, I want my independence be bounded by some entropy, right? And all of these constraints that I list here will still give me, they will also define a convex cone, right? So it might be degenerate, might be contained in some hypersurface, but it will still be some convex cone. And so the new global object, which I have to work with, will now be the intersection of the entropy cone with the cone of causal constraints. So that's the new global object I will be working with. And now the last step is to marginalize. So I take now a subset of all subsets. So I choose a set of jointly observable random variables, and I call this a marginal scenario, capital M. Classically, it's normally the case that a random variable is either observable or not, so that is the only constraint I have. Quantum mechanically, there are often constraints on which random variables are jointly measurable and which are not. So in quantum mechanics, we get more interesting marginal scenarios than in a classical situation, but in principle, it doesn't actually matter for this program. So it can treat both on the same footing. And then we marginalize. So we take this cone, this global cone intersected with the causal constraints, and then we just project it onto the axes labeled by those joint distribution that we have access to. That is geometrically trivial. I just take the cone and I throw away the coordinates I can't observe. It's algorithmically a bit more costly because, unfortunately, the cone is represented not in terms of extreme arrays, where I could just take the rays, cut away the coordinates I can't see, and then take the conal closure again, but it's presented in terms of inequalities, and marginalizing a cone that is specified in terms of inequalities is computationally not cheap. There's algorithms, for example, for Motzkin elimination, but they don't scale very well, and since the object we start with is already exponentially large, this only works for very small instances unless you add more structural insight. Okay, and the final result will be now a description of a marginal causal entropy cone. So the global one intersect causal constraints restricted to the marginals, and that gives me, since if we work with that Shannon cone relaxation, then this will be a polyhedral cone specified by finitely many inequalities, and that will also be true for this marginal cone, will also be polyhedral. So we get a list of entropic belt inequalities corresponding to the facets of this polyhedral cone. All right, so that is the project we've been pursuing since some time, and here are some things that are known about it. The first result that can maybe in retrospect be identified goes back to 88. It's an entropic CH-SH inequality, and I will explain what that means in a second, by Braunstein and Caves. And here there are no causal constraints. People didn't think about it at the time, maybe. But there is a non-trivial marginal scenario, namely the one that people know from the CH-SH type Bell inequalities, and which I will explain here for those who don't. So the interpretation is this. Let me explain my ad hoc notation here. So there are two parties, Alice and Bob, and each has two random variables, spin in x direction, spin in y direction, and it so happens that that not every pair of these random variables can be jointly measured. For example, and what you cannot do is you cannot measure two different random variables held by the same party simultaneously, right? So x Alice and y Alice together cannot physically be accessed. And what you can do, though, is, for example, observe the correlation between an x measurement by Alice and an x by Bob, y by Alice, and across. That's what you can do. And so let's first recall the standard CH-SH inequality. here, which says the following. So let's say we observe these pairs that are observable, and we find perfect correlation. Let's say these are plus minus valued random variables, and they are perfectly correlated along these black dotted lines. Perfect correlation here, here, and there. Then by transitivity of perfect correlation, we would expect that this link is also perfectly correlated. So I can't have plus, 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 and negative correlation. That's what I can't find. And if I cast this into linear inequality, I get this. So if I add up these black correlation functions, I subtract this correlation function, then this should be bounded above by a value of 2. Okay, so what Brownstein and Caves have shown is that if you take the very same scenario, but you don't plug in the correlation functions, you plug in the joint entropies, then you also get an inequality just with the sign reversed. And that was known by 88, and apparently was never pursued after that again, because people got started on this geometric description of Bell polytopes, and they thought this was more fundamental. There's a few things one can learn here. Namely, the first thing is that these entropic Bell inequalities, they seem to measure frustration in the degree of correlation rather than the sign of correlation. So here I said CHSH here includes the fact that includes transitivity of the sign of correlation. And here what this inequality measures is that you can't have the following situation, namely that these two are perfectly correlated, and uncorrelated. Right? Here it was anti-correlated, and here it is uncorrelated. So that can't happen either, right? And so, yeah, one thing that is was maybe an insight I found noteworthy when I first understood it is that not only we have frustration in the sign of correlation, but also in the degree of correlation, and they can also be violated by quantum mechanics. Right? So we can also have pairs of random variables that should be perfectly correlated, but actually are uncorrelated. I said before, this entropic CHSH resembles a sign reversed Bell inequality, and that's no coincidence, as we know since very shortly. I'll mention that again. Here's another way in which these entropic inequalities behave differently from what people may be used to if they have worked on quantum non-locality. Namely, it's an effect of concavity of entropy as opposed to linearity of Bell inequalities. And for example, the Popescu-Rohlich box is this hypothetical distribution which maximally violates the normal CHSH inequality, which indeed has perfect positive, and negative correlation along the black and red lines respectively. But it does not violate the entropic CHSH, because it doesn't look at the sign, but just at the degree, and the entropic inequality just sees correlation, so that's fine. So that's a bit disappointing maybe for people used to working for the non-locality. The most non-local object is not detected by this entropic construction. And now what happens is that there is a classically correlated distribution, such that if I take the convex mixture between the PR box and that classical distributions, I can actually violate the entropic criterion, right? So I have something that looks entropically classical. I mix in something convexly that is also classical. I get something violating this criterion. So yeah, just to keep in mind, these things work differently from the linear inequalities we are used to, and this actually can be generalized. Every non-local distribution can be activated entropically in the sense by just mixing the right classical distribution in. So now we set out to try maybe to replicate a lot of what has been done in the quantum non-locality literature, and so many simple scenarios are now fully understood. So we can, yeah.
Can you go back to the inequality? I thought the way you talked about these things, they should be homogeneous inequalities.
Yeah, they are. And this 2 is actually, it's actually the sum of 2 univariate.
Okay.
Sum of 2 univariate entropies. Okay. And then if it's binary, then I just put in 2 to make it simpler. So you can also do that here, by the way. You can also have here univariate probabilities if you set it up correctly. I mention that in a second.
Yeah, but the first one is true without any such assumption. The second one, you basically put in that the local
Yes.
entropy somehow
yes,
XA has entropy 1, no?
Yes, that's true. Yes, it's for binary outcomes. Yeah, you're right. Okay. Okay, so for example, if one looks at this common ancestor scenario, then again, I mentioned it was first treated in the machine learning community by Steudel and I in 2010, and they found one entropic inequality that is valid for this by common ancestor scenario, but not in general. This was tightened a bit later by Tobias Fritz, and as of last week, actually, not in version 1 of our paper from 2 weeks ago, but in version 2 from 1 week ago, this is now completely characterized. So we now know all entropic corollaries of that causal structure, and there are 3 classes of inequalities and their permutations, which completely characterize all information theoretic corollaries of having pairwise common ancestors, as opposed to a general dependency. Then to come back maybe to Andreas' comment, so, well, or maybe not quite actually. All right, so we see some similarity between these two objects. There seems to be some sign reversal, and this can be explained geometrically. What one can do is one can take the cone over the 2 outcome n variable probability distributions, so it's just some orthant, high dimensional orthant, and one can apply some linear transformation to it, which basically changes the signs, and then this linear transformation will embed this cone into the Shannon cone. And this means dually that every entropic inequality also can be turned into one that holds for 2 outcome Bell polytopes mod signs. So we can actually kind of explain why we see the similarity here. And even though it goes in the wrong direction, everything entropic also holds for probability distributions. These 2 cones seem to often share facets, so we can just look at binary Bell inequalities and try to prove whether they also hold entropically, and that seems to be a rich source of ansatz. So we have now entropic Bell inequalities for many observables per party, in particular these Collin-Gézin I22MM type inequalities, for those who can read the jargon.
So if you replace the H's with mutual informations, then do you get it with the same direction? Is that where this came from?
No, it's not where it comes from. It's a bit. I need to talk a bit about where it comes from. I can tell you later. It's a bit. In the end, it's some Möbius inversion that is involved that gives us a sign. Yeah, some combinatorial thing. Yeah. Okay, so that can be done. It can also. We also have entropic Bell inequalities for many parties. So I mean, all these things that people check for Bell inequalities, one can try to fast forward to that and see it all works here too. One interesting thing that we can easily do that is not so clear how to do it in the probabilistic setup is we can tighten all these bounds if a limit on the degree on the shared randomness is available. So if you say you want to test whether there is a classical model where there is only, I don't know, 2 bits of shared randomness, then this is easily incorporated here. Yeah, so and one thing to say is, of course, entropic, other than, I mean, here to make it look more similar to the inequality we know, I plugged in an a priori constraint on the number of outcomes, but of course, in general, as Andreas spotted immediately, these entropies are outcome size agnostic, and so it's not clear, for example, in the normal setup to have multipartite Bell inequalities with an arbitrary number of outcomes. That seems to be a very difficult problem, but here it kind of is included naturally, and that might or might not be an advantage. We don't really know at this point. Okay, so I'm almost done. Here's a few things we'd like to know. Okay, so I mean, one thing, of course, I find appealing here that somehow 2 different communities came up with the same problem. So the question is, are these ideas at all feasible to test for homophilia in social networks? And maybe one could be optimistic because the entropic information strictly subsumes conditional independences, so we use strictly more information than people used before with causal discovery algorithms. Of course, it's also more computationally intensive, so I don't really know. And one question that motivated this for Raphael, for example, is more recent developments in quantum non-locality. For example, people looking at the so-called bilocality scenario, which is basically a quantum mechanical version of that, where lambda 3 is removed. So the group here, Branchiat, Gézin, Pironio, they looked at a characterization of quantum experiments where there are two sources of quantum particles which are deemed to be independent. The question is, what can you learn about quantum non-locality in that setup? And there's, these entropic approaches seem to be tailored to encoding the independence that you have here, but there is not yet a very satisfactory quantum violation that can't be reduced somehow to bipartite Bell inequality violation there. So there's some stuff to be done there. And so these were practical desiderata. There's a lot of theoretical desideratas. I think what is bothering me most is that we should learn something about the computational complexity of deciding membership to these marginals. And they are not even obviously contained in NP. So somehow you can say I think maybe they should be simpler than probabilities because we coarse grain. Maybe that's true. Maybe they're even harder because, and the reason is, so how can you understand that it's not even clear whether the membership problem here is an NP? Well, if you compare to Bell polytopes, then the vertices of a Bell polytope are deterministic configurations. So the vertices have a concise characterization. And now if I have a general point, then by Kawase-Udari, it's a convex combination of not too many vertices, and all the vertices I can specify efficiently. So I can provide a concise characterization. But for entropic cones, it's not clear that extreme arrays, for example, if I wanted to try to generalize that, it's not clear that extreme arrays have an obvious characterization. If somebody claims to have an extreme array of an entropic cone, it's unclear to me how he would convince me of that fact. Right? So despite the similarity we saw between these Bell polytopes and these facets here of these cones, it's not clear how to use that computationally. And better understand the role of non-Shannon constraint. There is one scenario by Tobias Fritz, which actually is relatively small and is detected by a non-Shannon entropic inequality. And maybe, so I mean, that should be better understood. Maybe this is a simplified setting to hunt for classical, but also maybe for quantum non-Shannon inequalities. Maybe there are scenarios where already in relatively small marginal scenarios you can find something that might make the problem easier or not. And they,
Just about, these constraint inequalities. The constraint is such an conditional independence assumption, right? So they should maybe, this exists.
Yes, that could be true actually. Yeah, good point. Yeah. There you go. So didn't even think about that. Yep, it's right. Okay, here's my very short summary. So entropic marginals might turn out to be useful for causal inference, where quantum non-locality is, I would consider, some kind of a special case of that. So one could get the idea of studying them. And thanks for your attention.
I have a question. So you could also consider, if you have quantum states and you add this causality, so you say, well, this quantum state, whatever it is, must relate to this causal structure.
Yes.
Then are there cases where you say, well, then you cannot have a violation of the Bell inequalities in that setting because these?
Yes. All right. Okay. So that's of course a whole new class of questions.
Yeah.
So I mean, one thing is that the way I introduce it doesn't really work immediately quantum mechanically because the conditional independences played a certain role, and that's not so clear what that should even mean. Of course, you can say that graph I can reread as a history of how I created the state. I started with some state, I brought them together, applied some CP map at every node, and then what we get out is basically the structure people study in these tensor network states. Right? They can be thought of if there are no loops. They can be thought of having arisen from this way. It's still not the same, and the difference is that. It's kind of the difference between a Markov chain and a hidden Markov chain, right? Here, kind of, I want to have that no information of code passes through sneeze directly to wipe without being visible as sneeze, right? And this is not the case in these in tensor network states. So in that sense, I'm not quite sure. But of course, to say something positive, these Gézin-Pironi et al. Construction, of course, goes already in that direction. And the question is, what can you do there? So some people started looking at this. But it's not even clear what the right language should be. At the moment, they stand a bit apart from each other.
Further questions? Well, I had a little question about it since you were talking about this graphs. So you call it that Reichenbach's principle minimality. Is that because that would correspond to the minimal number of edges in the?
Yeah, the minimal number, it would correspond to the minimal number of predicted dependence and independence relations, right? So this universal godlike mover would predict more dependencies than you actually see, and so minimal in that sense. Yeah.
Okay, if there are no further questions, let's thank David again.